My name's David Rowe, VK5 Delta Golf Romeo. I've been involved in ham radio for about 30 years, and over the last few years I've been working on some digital voice work, in particular for HF radio. And today I'm going to talk about FreeDV, which is the digital voice mode that I'm developing with some other people. That uses a codec called Codec2. It's a special low bitrate codec. It's special because it's open source, no license fees, and it's something that can be experimented with if you want to. A little bit about HF radio and why digital voice is pretty hard over HF radio. And then I'd like to talk about the SM1000 smart mic. It's a little speaker microphone. You can plug into your radio and turn any HF or VHF radio into a digital voice radio. So you don't need to buy a special radio for it. And finally, a little bit about an SDR kit I've been working on. Okay, so this is your typical digital radio system. We take the signal from your microphone, regular ham microphone, through an A to D converter, and then we put it into a codec. The idea of the codec is it converts it down to some very low bit rate. For example, we run around 1300 bits per second for the voice coding over HF. Then we generally add some error correction. That's forward error correction, FEC, and that protects the voice bits, makes them a little bit more robust over the HF channel. Then put it through a modulator over the radio, then through a demodulator, which is sort of your modem. FEC decode, and then decode the digital speech signal, the low bitrate digital speech signal back to samples that we can then play out of your speaker. So the sort of boxes that we've been working on, I first started with the codec. I've got a background in, as well as being involved in ham radio, I've got a background in speech compression. So I wrote this speech codec, especially for the ham radio problem, in particular having an open source ham radio codec. I also have a bit of a background in modems, so we've written a modem, especially for HF digital radio. And I'm a bit weak in this area, forward error correction, but I've got a few guys who can help me, so I've been doing a bit of work in that lately as well. Okay, so FreeDV is an open source digital voice mode for HF radio. You can just download it in the form of a PC program, which I'll show you in a little while. And all the code is available for experimentation by hams or other people. It incorporates the codec, which does the speech compression, a special modem for HF radio, forward error correction, and all in a reasonably easy to use GUI program. A little bit of setup work, you need 2 sound cards and things like that to make it work, but thousands of people are using FreeDV around the world at the moment. It's now been integrated into the Flex radio software. I wrote an API for the FreeDV so that someone can just compile the software into someone else's SDR software program. Because it's open source, no license fees, no messing with that. Just grab the source code, compile it, and it's part of your latest radio project. So Flex have just released FreeDV mode with their software. And coming soon, we'll have the SM1000 speaker mic, which is an embedded for the FreeDV. I'm also working on improving the robustness of FreeDV over HF radio. Currently SSB works better on low signal to noise ratio channels than FreeDV, but pretty soon hopefully it'll be the other way around. We'll be able to get through using digital voice where you can't get through using SSB. Also interested in developing a VHF mode for this open source digital voice as well. That's just a screenshot of the FreeDV application that you can download from freedv.org. So got a waterfall in the middle. There's 16 tones or carriers in the waveform with a central high power carrier that's used for synchronization. So you can use your mouse to click to tune. You've got a signal to noise ratio measurement up here, works down to around 2 or 3 dB signal to noise ratio, and various other start and stop and options, squelch, etc. So when that's working, you basically get over HF radio noise-free digital speech. Yes?
Since that's multi-tone, how linear do your amplifiers have to be?
Yeah, you need it. Unfortunately, with this waveform, you need a fairly linear amplifier. We tend to back off around 12 dB, or 8 to 12 dB, so you'll maybe run 20, 25 watts through a 100 watt radio. That's very similar to actually what speech does. SSB has an average power level of 20, 25 watts for a 100 watt pet.
That's a non-compressed.
That's right. Yeah, you need to be careful to switch all that off because it needs a fairly linear one. The new waveform we're working on has got some compression built in, so hopefully we can push it a bit higher if your amplifier is rated for a higher average power. That is an issue. We're losing a few dB there. So yeah, FreeDV combines an open source HF modem and Codec2. It's a desktop GUI application. It's cross-platform. I come from a Linux background, so we wanted to make sure it runs nicely on Linux and the other open source operating systems, but most people do use it on Windows. And it allows any SSB radio to be used for HF digital voice. You do need a couple of sound cards and a bit of patience to set it all up, but quite a few people use it. It's become quite popular over the last few years. So all of this, as I mentioned before, is open source, and I just wanted to say a little bit about why that's important. This is also, as well as ham radio operators, this is also targeted at just general purpose HF radio. There's a lot of HF being used for humanitarian work in the developing world. So HF is still the only way people can get messages or voices from A to B in some fairly critical areas of the world. So it's nice if we can have a open source software and hardware that can deal with that sort of communication problem without needing really expensive licensed systems. So as we all know, one of the advantages of HF in humanitarian areas is no infrastructure. You know, you can bounce signals around the world from point to point. It can be fairly low cost at the moment. If you want to set up a Codec radio in the middle of nowhere, it's sort of around $10,000. But we believe a lot of that hardware can be replaced with software. We can get it down to a couple of $100s. For people, hams and hackers who are interested in open radio, one of the main things is when all the software is open, you can tinker with it, you can modify, you can improve. It's not locked down. Other codecs that are locked down, it's actually illegal under the licensing agreements to modify them in any way or have a look inside them, which is kind of against the the ham ethos. I've got a few slides now to talk about speech coding, because that's usually speech codec is a black box that we don't know too much about, and I like to explain. One of my jobs I see is to explain what's going on so other people can understand what's going on inside the radios. So speech coding or speech compression, we take speech samples, for example 16-bit samples that have been sampled at 8 kilohertz. We then compress it down to a very low bit rate, such as 14 or 2400 bits per second or even lower. It's the art of what can we throw away. There's a lot of redundancy in speech. A lot of that you don't really need to get to be able to understand what's being said. So there's two aims of speech coding. One is to retain intelligible speech. That means you can understand what I'm saying. And the other is natural speech, which might mean you can identify who the speaker is. They don't sound like a robot. You can tell if they're a man or a woman or what have you, or that it's your friend or not your friend. So a good speech codec will retain intelligible speech and natural sounding speech. And what we do for codec2 is we use a model of speech to compress it, and then we send the model parameters over the channel. So what I mean by a model is, as I'm talking, my vocal tract is acting like a filter, just like a filter you'd have on your radios. And that filter is varying as I articulate the sounds, but it's actually quite a good model for your vocal tract as a 10th order filter, just like you having a 10th order filter on your transmitter. So what I can do is say, okay, there's a peak in the spectrum here, there's a peak in the spectrum there, and I can send that information about the filter over the channel rather than trying to code the actual waveform of what I'm saying. And it turns out when we use model-based speech compression, sending these model parameters over the channel, you get a much higher compression rate than a waveform coder. It doesn't sound quite as good as a waveform coder, but you get better compression rates, and that's what we're all about for our application.
Could you mention a couple of common, like a model-based one versus a waveform one that's a bit of a range that we might have commonly heard of?
A waveform-based one would be 64 kilobits per second PCM that we use on our telephones and our landlines. They get compressed by the exchange. A model-based one, or one that's in between, would be MP3s. That uses a model of the human auditory model. There is noise in MP3s, but it's masked. They have a model of the ear rather than the vocal tract. Yeah. So that would be a model-based one. Your mobile phones use hybrid waveform, a mixture of the two techniques to get sort of good toll quality communications. Pure model-based one, the D-Star codec, AMBE. As you get into radio, you need these lower bandwidths, so they tend to be all model-based. So just to talk about models a bit more, one example is of a model parameter is the pitch of human voice. And for humans, that's in the range of around 50 to 500 hertz. A male bass, very low pitch speaker will be around 50 hertz, and a female or child would be around 500 hertz. It turns out that you can accurately represent the pitch with about 7 bits of information. So if we send the pitch parameter every 20 milliseconds, that gives you around 350 bits per second for the pitch information. You have to keep sending it because the pitch changes as you talk and articulate the sounds. So you just can't send it once. So I'll just illustrate how that pitch would work and how sinusoidal speech coding is the name of the model that I use for Codec2. What we're really doing is we're just using a bunch of sine waves to represent the speech signal, and I'll show you how that comes together. This is a little snapshot of speech. It's around 320 samples or 40 milliseconds of speech from a female speaker. Now you can see the amplitude slowly drifting upwards across the frame. The amplitude's changing slowly. But you can also see that the waveform repeats itself as these... oh, I can't see my mouse there. There it is. So you can see that sort of repeats itself here, repeats itself again. So it's repeating itself every 35 samples or so. And that period that it takes to repeat is called the pitch period. So in this case, that's about 4.4 milliseconds, or about 230 hertz is the pitch of that speaker at this instant in time. It changes over time. So it's periodic in the time domain, repeating itself. Now if we look at the spectrum, this is just like you'd see on a spectrum analyzer. Along the bottom we've got frequency, up the side we've got amplitude in dB. You can see that once again it repeats itself in the frequency domain. You see these spectral lines here, they repeat themselves at the same rate as the pitch period. So every 230 hertz we get one of these lines in the frequency domain. The amplitude is varying again, up and down, and it turns out that these peaks in the amplitude, here and here, are how we understand speech. It's these resonances in the speech signal that our ear picks up. And our ear actually operates in the frequency domain. It's like a bunch of bandpass filters. So periodic in the time domain, periodic in the frequency domain. Get these impulses. So these are all harmonics of the fundamental down here at 230 hertz. So what we do is for sinusoidal speech coding is we'll say, well, that looks like just a bunch of sine waves, all 230 hertz apart with different amplitudes and phases. So we can model the speech as a sum of sine waves added together, all within different amplitude, phases and frequencies. And we only have to send one frequency, which is the pitch, because we know it repeats itself every 230 hertz. So there's a bunch of compression right there. We don't have to send the frequency of every single one of them. The amplitudes are fairly slowly varying, so we can just say send the differences between harmonics to efficiently encode them. And for low bitrate speech, we throw away the phase and we just use some rules to sort of synthesize it at the receiver. And here's an example of actually synthesizing some speech using this sine wave model. Up the top we've got some original speech. In this case it's a male speaker and he's got quite a long pitch period. One starts here at around sample 100 and ends here. It starts again at around sample 200. So this guy's got a pitch period of around 100 samples, which I think is around 80 hertz at the moment. Now what we can do is we can take a bunch of sine waves that are multiples of that fundamental and start adding them together and see what happens. This is just one sine wave. That's another one. And that's with 10 sine waves. Now you can see the pitch structure starting to appear. It's offset in time from the original at top, but you can see here's the start of one pitch period, here's the start of the other one, and some of this structure is starting to develop. That's with 10 sine waves. 25 starting to look quite like the original, and that's with the full 4 kilohertz spectrum worth of sine waves, or 50 of them in this case, and that's the synthesized speech looks very close to the original. So that's an example of how we can synthesize speech using this sine wave model. So typical bit allocation for the codec is we'll have 36 bits for the amplitudes, which was that slowly varying, that red line there basically. If you sample that red line, that's the amplitude information. So we use 36 bits for that. 5 bits for the frame energy, and that's kind of like the volume, if you like, the gain of this frame. And then the pitch I already mentioned, 7 bits, and something else called the voicing, which describes whether the that particular frame is a consonant or a vowel. Consonant tends to have noise-like structure, and a vowel has this periodic sine wave structure, and that's called voicing. So every 40 milliseconds we update those parameters because they change over time, and then we transmit them over the channel, which gives you around 1300 bits per second for that particular codec2 mode. So I've got some samples now. This is an example of codec2 at various different bit rates. I'll start with the highest and go down. It's just a little bit of text from a little bit of speech from a ham radio operator. We'll just wait for the movement to stop. Okay. First of all, the original.
W5ABC, here is Victor Echo 9 Quebec Romeo Papa. My name is Bruce, Bravo Romeo Uniform Charlie Echo.
Okay, now at 3200 bits per second.
W5ABC, here is Victor Echo 9 Quebec Romeo Papa. My name is Bruce, Bravo Romeo Uniform Charlie Echo.
Now 1300 bits per second.
W5ABC, here is Victor Echo 9 Quebec Romeo Papa. My name is Bruce, Bravo Romeo Uniform Charlie Echo.
And 450 bits per second.
W5ABC, here is Echo 9 Quebec Romeo Papa. My name is Bruce, Bravo Romeo Uniform Charlie Echo.
Okay.
So 450 bits per second, what channel width does that fit into?
A couple of hundred hertz.
It's amazing.
Yeah, if it was QPSK. Yes.
Well, what was the first one we heard? What bit?
The first one was 3200.
Okay, and that sounded quite normal, didn't it?
Yes, or there's the original first of all, then 3200. I'll play them again.
W5ABC, here is Victor Echo 9 Quebec Romeo Papa. My name is Bruce, Bravo Romeo Uniform Charlie Echo.
Now 3200.
W5ABC, here is Victor Echo 9 Quebec Romeo Papa. My name is Bruce, Bravo Romeo Uniform Charlie Echo.
1300.
W5ABC, here is Victor Echo 9 Quebec Romeo Papa. My name is Bruce, Bravo Romeo Uniform Charlie Echo.
And 450.
W5ABC, here is Victor Echo 9 Quebec Romeo Papa. My name is Bruce, Bravo Romeo Uniform Charlie Echo.
Just quickly, Dave, what is a D-Star handy typically running at?
2400.
2400.
So you're better than D-Star.
We like to think so. In fact, I've got a comparison here for D-Star, if you like. This is comparing some different speech codecs that are around. I'll play the original codec2 at 1400 bits per second, and then a few other codecs. I'll announce them as I go. So first the original.
Navy attacked the big task force.
Codec2 at 1400.
The Navy attacked the big task force.
Ambi.
The Navy attacked the big task force.
And this is MELP.
The Navy attacked the big task force.
MELP's quite common as a military standard, yeah, but closed source. And this is an old school LPC-10.
The Navy attacked the big task force.
That was a 1970s MIDI standard. So I'll play them again. Original.
The Navy attacked the big task force.
Codec2.
The Navy attacked the big task force.
Ambi.
The Navy attacked the big task force.
MELP.
The Navy attacked the big task force.
And LPC-10.
The Navy attacked the big task force.
Now Codec2 was operating at 1400, MELP was 2400, and Ambi was 2000 bits per second there, so significantly lower. One problem with speech codecs is they don't work very well on non-speech signals, such as one good example is background noise. So what they can do is interfere with some of those model parameters. The codec can get confused. So I've got an example here of a sample with truck noise, which I'll play then through Codec2 and through an old LPC-10 vocoder that shows you what happens when they go wrong. So this is original.
It's easy to tell the depth of a well.
Codec2.
It's easy to tell the depth of a well.
And LPC-10.
It's easy to tell the depth of a well.
what happened there with LPC10 is the pitch estimator got confused by the periodic truck background noise. So that's something you have to design for as well, because people want to use these things in mobile situations. Okay. So the whole reason for this work is to do some digital voice work. Traditionally, speech codecs have been used for other things like mobile phones, and they operate off pretty wide bandwidths. They've got lots of spectrum available, high bit rates if they need them. But over VHF and UHF radio, the spectrum for digital radio is really limited. Plus, it's a really nasty channel, especially HF. Lots of noise and bit errors, frequency selective fading. If any of you have tried data over HF, it's a lot harder to get through than, say, SSB. So we depend on getting data through our channels to make digital voice work correctly. But there is quite a lot of interest out there, if we have the right sort of codec and the right sort of quality over the channel. One of the advantages of compressed speech is that you have less bits per second over the channel, so you can tend to get better performance for a given modem. If you operate at 1200 bits per second rather than 2400, you've got twice the power available for every bit, so that tends to get a better chance of getting through. Lower bit rate, you also have less transmitter power, which saves battery and can improve the speech quality. One really important thing to understand is that voice is not like data. A lot of our digital work, say getting a packet off a website, you want that packet to be perfect. It'll get thrown away by the IP stack if it has a single bit error. We don't really care with voice. There's a few bit errors in it. You'll hear a few beeps or clicks or something, but you don't really care. It'll still get through. Even if you throw away 20 or 100 milliseconds of speech, this happens in SSB all the time. You get fade. You lose a second or so, but the conversation keeps on going. So there's a real tendency for a lot of people to treat digital voice like data and have ARQ or perfect forward error correction, etc. But you really don't need to. And by throwing away that assumption it needs to be perfect, you can get big improvements in how well the system works. HF channel, it's really good for long distance, no infrastructure, but really bad for data and digital voice. You need to throw a lot of power at the channel to get a low bit error rate, and that's why often when people are doing data using PACTOR, things like that, you need quite high power or quite good channels or lots of repeats. One kind of frustrating thing for me is how well analog voice really works, and I've only just sort of discovered this, but I've been trying to compete with it. SSB works really well, and I've by studying how SSB works and comparing it to digital voice, I've sort of learnt some ideas to how to optimise the digital voice systems. One example is that I showed you before that speech spectrum, and it had those peaks that were important for speech perception, for us to understand what's being said. Now, it just so happens is when noise increases on SSB, so those peaks are the last things to go because they're right at the top. So as your channel gets weaker, the HF radio SSB has perfect allocation of power to the most important parts of the speech waveform, which is kind of neat. It probably wasn't intended that way, but it's one of the reasons why it sort of works so well. So analog SSB is actually really hard to beat, especially when there's fading. This is an example of that modem signal. In this case, it's a horizontal waterfall diagram, and you can see the bright area is a high signal, and the dark area is, for instance, through here, great big fade where the whole thing gets wiped out. And you're always getting something going, like you might be getting a strong signal here, but a really weak one over here. Strong signal here, weak one there. So there's always bit errors in this thing, and often they're reaching 10% bit error rates, which is really high for a digital system. There's no digital data systems that will run at 10% bit error rates. They like one error in a million. That's the sort of error rates digital guys like.
Just a question, are you going to talk about FEC?
Not a lot today. Not a lot.
Tell us a little bit about what FEC you're using.
I use some partial protection using a GoLay code at this point, and the new stuff's using LDPC codes. Yeah.
What type of codes?
LDPC, low density parity check codes, which are near capacity codes, so nearly as good as you can get. But unfortunately, I don't have time to go into all that right today. Also, analog has lots of redundancy. So if you lose part of my speech spectrum due to that selective fading, you'll hear the other part come through. So you'll be able to understand what I'm saying. Whereas digital has global bits. If that pitch gets messed up, it affects the whole spectrum. So that's a little bit analog has a little bit more redundancy built into it than, say, digital. One interesting thing, though, on digital voice is that different bits have different importance. You don't really have to protect with forward error correction every single bit in the packet. Some of them can handle quite a high bit error rate and you can still understand. Others are really critical. So what we can do is have partial protection of some parameters. That means we don't need to protect everything with forward error correction, which keeps the bit error rate down. Some other issues in speech codecs, many of them, such as the ones that you use for your mobile phone, they have memory. So if something messes up in this packet, you'll still be hearing the results down here because there's a memory in the codec that takes a while to go away. Analog speech doesn't have much memory. You know, once you've said something that's been wiped out by a fade, the next part of it sounds just fine. The other good thing about analog is you get this gradual decrease in quality with signal to noise ratio. It doesn't reach that point where it just falls over. And as I said before, it applies power fairly intelligently across frequency and time. The modem that we use uses the same amount of power for silence as it does for important parts of speech. Whereas in analog speech, your power amplifier is doing nothing when there's silence, and you use the full PET power range when something comes in. So it's got a really intelligent allocation of power over time. But one of the nice things about open source is that it gives us a few more knobs we can turn to optimise our systems. If we were using a closed source codec, we'd have no choice about what that codec does. We have no knowledge of what the different bits do inside that codec, which ones we should protect, which ones we shouldn't. Whereas what I did was when I had trouble with HF channels, I redesigned the codec to be more suitable for HF channels. So that's one nice thing you can do with open source. And I'm experimenting by mixing and matching between the modem and the codec to optimise things.
David,
yeah.
Do you use any time diversity for HF?
Not yet, not in the current mode, but looking into that for the next one, some interleaving, yeah, just over a short period. The issue with that is latency.
Yeah.
You can't talk, for push to talk, you only want a few hundred milliseconds of latency. You don't want to have to wait a second or so for the digital voice to come out the other end, yeah. Okay, so the goals, as I said, FreeDV, the software program, the initial modes, was released around about 2 years ago, and it's been running fairly happily for the last few years. Quite a people experimenting, playing with it. It doesn't quite work as well as single sideband, and you still need to have a laptop and sound cards and things to use it.
At both ends?
Yes, at both ends, yes. Although some rig manufacturers are getting onto it, Flex have released it inside their software now. However, so one of the goals for this year was to try and make it easier to use. So we decided to develop the SM1000, which is a speaker microphone. It's got a little microphone and a speaker. This is the very first prototype. And the idea of this is you can just plug it straight into any HF or VHF radio. It's got the standard sort of RJ45 that a lot of radios use, plus 3.5mm jack, so it'll hook up to virtually any radio through the microphone and speaker ports. So you talk into the microphone on Smart Mic, or the SM1000. It then compresses the speech. It then generates the modem tones that go into your radio and get transmitted over the air. It's got a push-to-talk button on the side that triggers the transmit relay in your radio as well. So it's basically just like using a regular push-to-talk microphone, but now it's all digital, up and back. So it's the full FreeDV implementation that we normally do on a computer in a little embedded device.
Very good.
It's in, basically the beta units will be coming out in a small metal box, so we're not quite sure if people are going to use them as a microphone or a box on the desk with their own headset, but we'll see how that goes. It's been developed by myself and a US ham, Rick Barnich, who's done a great job on the CAD work. I've done a lot of the software and debugging, and we're getting them manufactured by a Chinese company that I've worked with before.
Excuse me, David, is it firmware upgrade?
Oh yes, yes. It's all open source, hardware and software, so you're welcome to play with it, do your own and program the firmware. It uses a little microcontroller, it's all in C. Yes?
How much adjustment will you have to make on it to set it up?
There's things like levels you'll need to tweak.
Yeah, how many?
There's a mic gain for your transmit. It's not very sensitive on receive, so that'd probably be about it, really.
Yeah, I've played with the AOR voice box. That had 4 on it, and it was very sensitive to changes in volume of the voice and that on transmit.
Yes.
You can get a lot of signal breakup if you changed your volume of your voice.
That's the outgoing audio level. Yeah, they can be pretty sensitive to clipping if you hit the peak value. Yeah, but that's one of the things I guess we'll be looking for people to give us feedback on as well. So, yeah, built-in rig interfaces, microphone, speaker, it's all open and should be available within about a month. This is the current setup you need, and this works pretty well. You have some sort of rig interface box to a HF radio with a headset and a PC. That's how people are using it at the moment. It is quite fun to use. You know, the GUI displays are nice as well, and you get a lot of information off the channel. And a bit of activity on 14.236, in particular in the US. People are doing transatlantic communication on it now between Europe and the East Coast as well, East Coast US. We have heard it here too from the US guys.
Actually, you could use it to replace Echolink.
Dave, how can you actually recognise the signals? What would they sound like if you haven't got your own?
I have to play one to you. It sounds a lot like a modem, and it's 16. If on the spectrogram or the waterfall, 16 tones wide with 2 strong sensor carriers that are 3 dB above. Yeah, I think there might be some examples on the freedv.org website of what it actually sounds like.
There's a website too, so if you're interested, people will maybe post that they're on air and where they're listening or transmitting, so you kind of...
That's right, it's a QSO finder that if you're interested in finding where people are or having people call you.
What's the 20 metre frequency, Dave?
14.236, yeah.
Right, sort of SSTV.
Now, during your presentation, you talked about fading on HF a lot. Typically what you get on HF is either natural noise in terms of a distant thunderstorm, so you get lightning crashes, and you also get local noise, which is generated by your neighbour's TV, switch mode, power supply, blah, blah, blah. So how's it going to cope with the natural and man-made noise?
If you're above the threshold signal-to-noise ratio, you won't hear any of them. Okay. You'll get silence and digital voice. That's the great advantage over analogue. But those background noise sources, your plasma next door is S9, well, you'll still need S9 or a little bit in your receive FreeDV signal to be able to get it. And analog, even as you increase the signal-to-noise ratio, you always get that hiss in the background still, whereas this is complete silence once it's synced up. So why do we want embedded? Well, currently you need a laptop and sound interface. There's a bit of frustration out there about people having to buy new radios to run proprietary DV modes. This sort of stuff can run on legacy radios, so you can repurpose what you've got and not be forced to stick with this particular mode or that particular mode. It's all programmable, so if someone comes up with something new, go for it. Nice small form factor, portable. It only uses a couple hundred milliwatts, so it'll run off soda work, that sort of thing, quite happily. And it makes setup a little bit easier than the current system. And I guess it's a way to get wide adoption of this technology. Just technically, what's inside is one of these little microcontrollers, STM. It's an ARM4. It's the sort of processor that you'd find in your router, like your internet router at home, but it doesn't have an operating system. It's just running bare metal. One of the great things for us is it's got a floating point unit, so it can do all the DSP calculations efficiently, and we just really had to recompile the stuff that was running on the PC, and it just sort of worked with just a little bit of optimization. This chip has a bunch of peripherals, like onboard analog digital converters and digital analog converters, so we don't need any external ones. We just feed those into the line interface circuits, and we got it all to work okay with a little bit of noise reduction. They're not an Arduino. It's a 1500 page data sheet, and it was a bit of just to get that first blinky going on the thing was quite a bit of work. But once you get it going, it's not too hard. It just uses the GCC toolchain, so all open source tools. If you want to play with this chip, they're $18 for the development boards, quite powerful for what they are. And they're really popular in SDR designs. A lot of people are coming up with standalone PC-less SDRs using these particular chips with a little touch screen and things like that, because they've got that sort of signal processing capability. And it's plenty for this narrowband ham stuff, 5 kilohertz wide channels. You don't need an FPGA or intensive processing. One of the challenges we've got with the SM1000, there is no GUI, so we've got to make sure this thing can work without all the fancy waterfall diagrams and things like that. Fortunately, it can automatically handle fairly large frequency offsets, a couple of hundred hertz, so your tuning doesn't have to be spot on. Much looser tuning than single sideband, for example.
Does it have any lights? I mean, is there a tuning light or something?
Well, we've got LEDs and that, but they're soft. We haven't quite worked out how we're going to drive all that yet.
Clipping light for the mic and
yeah, there's a clipping and error LED that blinks when you know you're getting a few errors instead of a signal to noise ratio readout. And there's a clipping to tell us that you're overdriving the thing.
Oh, good.
But yeah, haven't quite worked out if we need tuning aids. My hope is that once you've tuned it once or twice, you'll get close enough and it'll just go bang and start working.
Once it's locked on, will it handle a bit of drift?
Yeah, drift. It can handle about 1 hertz per second, so you can use a VFO or something and it won't have a problem. And plus or minus 200 hertz at acquisition. Yeah. And it syncs up quickly, like 100 milliseconds, 200 milliseconds. It's like using analog radio. Yeah. Low power and all open source. Oh, it also has a pass-through mode, so you can if it's hooked up to an SSB radio, you can disable the DV and use it as a regular microphone, just as analog pass-through, so you can go back and forth without having to disconnect everything.
How will that be switched?
It's done in software.
They double click it.
Oh, yeah, it's like a mode button.
You'll have a button.
Yeah, there's a couple of mode buttons and LEDs, so even if you're in the middle of a call and you want to hear what the off-air signal sounds like, you can press the button down for a moment and hear the modem tones let go and you're back to DV. And likewise, you can just cycle through the mode to go from digital to analog.
Going back to the AOR again, you need to tap to the combination of clicks on the microphone.
Oh, okay, yeah. I've heard about the AORs, but I've never actually had to use one. Yeah.
Difficult to set up.
Yes, and the long sync sequences were.
And the dipping was a big factor.
Yes. Yeah, there's a team of guys in the States who have been playing with equipment like that and digital voice for 10, 15 years, and we've taken a lot of feedback from them on how to make this work properly and try and avoid some of those sorts of issues.
So they go back to the modem.
Yes. One other little technical detail is this doesn't have any operating system on it. I've been doing a lot of embedded Linux work, and I thought that was pretty good, but I really like not having an operating system. It boots like an analog radio, like you apply power and decoded digital voice comes out. None of this boot sequence that even I've got to put it with on my phone these days. No 300 megabyte build systems. If you're trying to build embedded Linux or something, it's a massive big build system. It's fast, tiny little programs that build quickly. Internally on a system with an operating system, it's forever swapping because they're multitasking. They're swapping tasks all the time, and that's a killer if you're doing DSP because you're halfway through doing some filter and it takes off and tells the time or something, or serves runs the web server for a few milliseconds. So it's really nice to have not that going on, and at a lower level what's happening there is the instruction cache is being thrashed, so your programs are falling out of high-speed memory, which means bad performance. So yeah, I kind of like not having an operating system. The only problem is it's sudden death. Something goes wrong, it sits there on the desk, it doesn't do anything and tell you. So you've got to sort of get over a few hurdles and work out how to debug things. And poor connectivity, there's no IP connectivity or anything like that. It does have a USB port, and I've done a few little test programs on that, but haven't done anything with it yet, except for reflashing. So the status, we've ported the FreeDV software, got it running, transmit receiver. If you look at the website there's blog posts of it running and decoding signals. We've just completed, this is the prototype, there's a bunch of little changes on that, and we've also made some changes to make manufacture cheaper. So the Chinese guys will say, can we use this part rather than this part? And we'll look at it and say, okay, but it means we need to change the footprint. So a bunch of little changes. They've all been done. Right at the moment, we're having a couple of beta units manufactured. Should get those within 2 weeks. I'll test them out and then push the button for the first run of 100. And the next project Rick and I'd like to work with is combining this with a software-defined radio. So you'd have an open source digital voice software-defined radio. They can also do analog voice in all your regular modes as well. Because we've worked out that the SDRs are so simple now that we've actually got most of the bits we need already here. We just need the mixer and the local oscillator because we've got microphone, speaker, the signal processing in the microcontroller. The signal processing we need to do for a HF radio is nothing compared to what we're already doing for digital voice. So it'll just run in a few spare MIPS.
There'll be no PC in that thing?
No PC, yeah. And probably a touch screen or something like that. And, it could be for $100, something like that, maybe or a couple of $100, a full embedded HF SDR. It's completely open. You can program it as much as you want.
Do you have any sample of female voice?
I do, and I've run quite a few through it, but don't have any I can get to easily right now. Yeah.
Now with your SDR, it will be a transceiver?
Yes. Yeah, we'd like to put a PA on it and filters and things, so 20 watts, sort of that sort of power output, sort of KX3 type, or a bit more than that type power levels. Yeah. The new modes that we're developing for FreeDV won't need a lot of power to run. Some of them we're having to wind the power right down to test them properly and down to a few watts, so hopefully it'll work quite efficiently at low power levels.
So the transceiver, would that be like 50 megs, 30 megs? What's if you have
yeah, probably initially there's two things I'd like to do. One's a HF one and one's a handy talkie, so like a 2 metre or 70 centimetre radio that could pretty much be this, but just with a Class C amplifier and that sort of thing. Yeah.
With the interfacing to the rigs, do you have jumpers for different types of rigs?
Yes, there's a little patch panel there that you can just move wires between. Yeah, and it's got a bunch of different I/O, RJ45 3.5mm jacks, so similar to the patch panels and things used in some of the rig interface boxes. Yeah.
Just a quick question: when you're going to be aiming for VHF and UHF, bypassing preempsis and deempsis and all that's fairly common. Obviously with a HF this is easy, we can plug it into the mic connector or the accessory connector at the back, whereas when you go into a legacy VHF radio, so where are you guys?
Yeah, good question. It's something we need to look at the moment, and I'm currently doing some work on checking out what all those preempsis and deempsis does, and can we use existing legacy radios just through the mic connector, or can we really, is there nothing that can be done? Because there might be some signal processing we can do to overcome that. The other thing we can do is lower our bit rate. D-Star operates at 4800 over the air. We can get away with less than 1000. So,
so
we might be able to run it.
A sweet spot somewhere in that.
We might be able to make it run through legacy rigs at maybe a lower quality, but it might have a better signal to noise ratio and go 4 times as far or something. Yeah, all these knobs we can twiddle because it's open source.
David,
yes.
Source code on the website?
Yes.
Yep.
Yes. Source code for even down to the printed circuit board and CAD files for the box. Yeah. Just one final slide on a club sort of SDR radio. That's we call this thing Open Radio. We wanted a radio that could be built in a few hours in a workshop for people who aren't really hams or into radio, but just to get them started. So this is a sort of soft rock clone. It's just a low power transmitter and receiver. It can transmit PSK31 and FSK at about 40 milliwatts, enough to go across the room, do chat, things like that. And it's a HF radio, 100 kilohertz to 30 megahertz. Typical sort of Silicon Labs sort of oscillator chip, Taillow detector, that sort of thing. Plugs into regular SDR software on your PC. And we've gone to a lot of extent to make it easy to assemble. So we've used the minimum of surface mount, but we want some surface mount because we want people to have a go at it and see how they go. But they're large 1206s and things like that. A few coils you've got to wind, like a little transformer, and optionally some filters, because we want people to have a go at winding coils. But it's a binocular core from JCAR rather than a toroid. And it's got a little Arduino for control, so you plug in your USB to do frequency control, and you plug in your audio there. And there's a couple of these being built now. We're getting kits made. They'll be available in December, $50 US. And it can be built with, I built one in 2 hours and was tuning in hams and things like that night. And transmitting PSK31 across Adelaide on 40 milliwatts, which was kind of cool.
So that board, who can get that board from?
Openradio.net.au. Down the bottom there's the website, and they're being kitted up by a Chinese company that we're working with. So great for a club project at hams or even schools. We're doing it at a Linux conference. We're going to get these guys into radio by building something like this. And that's the end. Thank you.
Very good.